All right, so remember that this week we will finish up, today we'll finish up talking about strings. We'll go over a little bit of debugging, and then I will devote as much time as possible. Then we'll finish up debugging on Wednesday, but I'll devote as much time as possible on Wednesday to a review. And primarily that will take the form of me bringing in last year's midterm exam and doing it in front of you so you can see what it looks like. It'll be about the same. Nowhere near as challenging as even a hack or an assignment. It'll be something simple, something familiar that you've done before with a little bit of a twist. I haven't written it yet, so I can't tell you what that is. Remember, it is open book, open note, open computer. In fact, it's required computer because it's a live coding exercise that you'll code as you'll write your program on your machine. You will submit it to the web hand-in like normal, like any hack, like any assignment. There will be a grader. You can run the grader as many times as you want in that hour and 15 minutes that you have. You can resubmit as many times as you want. Whatever is in there by the end of that time, 6:15 on that Wednesday, then that's what we'll be grading. Remember, it is about 10% of your grade, so make sure that you are well prepared for it. The best preparation that you can make for it is by making sure that you've done all the hacks, that you've done all of the homework, and get a good start on homework 3, which is due that week. So don't wait until Thursday to get started on homework 3 because the midterm covers stuff that is on homework 3. All right, arrays. We do not cover strings in the midterm, but everything up to and including arrays. Okay. But it would be fair. We're not going to put it on the exam, but it would be fair game because remember that strings are nothing more than character arrays. They're an array of char values. The first character, the second character, the third character. The biggest difference with a string is that it has to be null terminated. The null terminating character is that /0. And if you look it up on the ASCII text table, it does have a value of 0. It's not the same thing as 0. It is the null terminating character. That tells you when the end of the string is. So that if you have an array of size 100, you can still have an array, you can have a string of length 5 in there with a null terminating character after it. The rest of the space, you're not using it, but it is still there. So you can have a string that is shorter than the array that actually holds it. Okay? Remember that if you do not have a null terminating character in there, it is undefined behavior. So you have to be careful when you're processing strings, especially if you're using a function that is part of the string library, because if you have to read the documentation to see, does it take care of that null terminating string for me or not? Do I have to potentially take care of it myself? All right? Let's go ahead and jump ahead here. Again, we have already seen one such operation. This is the example that we went over last time, where we did a deep string copy. We created a new string using malloc, and then we used this built-in function in the string library strcpy. Remember what that was short for? str is short for string, cpy, just take out the O, and it's copy, right? It copies the second argument into the first argument. So why is it kind of backwards like that? Well, it's copying the second one into the first one. It looks like an assignment, right? In x equals 10, it's taking the thing on the right-hand side and putting it into the variable on the left-hand side. So it follows that same pattern. Remember, however, that you cannot do something like this. Copy is equal to whatever, right? Chris. That after you've created a string, you cannot use the assignment operator. You can only use the assignment operator at declaration. Instead, you need to use strcpy. Okay? So let's go ahead and pick up where we left off by looking at some more of those functions that are provided to you in the standard string library. So string processing. Right? Again, the string library is located where? String.h. The string.h library provides many other useful functions. I'm not going to go over them all. There are dozens upon dozens of them. So anytime you think, oh, I need to do this operation on a string, go to the documentation. Is there a function in there that's going to help me? So just simply Google string.h and see what's in there, or use the man pages to do so. One of the ones that I want to look at is string concatenation. Example, STRCAT. Right? This is string concatenation. Right? So what is concatenation? Nation is taking appending one string to the end of another string. Right? And that's basically what it is. It's a fancy word, concatenation. Let me go ahead and open up REPL here and demonstrate it. Should have opened this up to begin with, but that's OK. Let's go ahead and get rid of this. Increase the size so we can all see. So let me go ahead and create a string here, char, and then I'll make it into a static string, say full name, right? And I'll make it of size 100. What I'm going to do is I'm going to make this into my full name, my last name, comma, space, first name. Now, I could do that directly if I really wanted to by simply just doing strcpy into full name, Burke, comma, Christopher. There we go. And certainly 100 characters, that is large. That array is large enough to hold this many characters. But what I want to do is I want to do that piecemeal. So I'm going to demonstrate concatenation. So what I'm going to do is I'm going to start out by copying into my full name, my last name, just simply Burke. Right? And let's print it out, printf. Remember what the placeholder for a string was? %. Makes sense. It's one of the few that makes sense. %s, end the line, full name. Right? Now at this point, it's just, oops, what else? What am I missing? The standard input string library and also the standard library. I should probably bring that in. There we go. There we go. There's my last name, Burke. Okay. Now what I want to do is I don't want to overwrite that information. Burke is in there right now. What I want to do is I want to append at the end a comma and a space. So to do that, I could do it manually, right? I could go ahead and do like full name of, let's see, 0, 1, 2, 3, 4, 5. So the next one would be 6. I can set that equal to the comma. I can go full name of 7 is equal to, and you can see already that this is going to be tedious and error prone, and you don't want to do it this way. And of course, I would have to take care of the null terminating character manually. Instead, what I want to do is I want to append or concatenate a comma space. Right? And to do that, I use STRCAT, and it follows the same pattern. The second argument, you're going to concatenate that to the first argument. So you're going to shove these two things together, making a new string. So full name, I'll concatenate, comma, space. Right? Now note here that these are two characters. You cannot put a single quotes around this because these are two characters. Single quotes are for single characters. Even when you've got an escape sequence like this, that's a single character. It's not two characters. The backslash is just simply escaping that out. So let me go ahead and restore this to comma space. Right? And then I'll print it out again and show you that oops, copy. And there we go. And show you that it prints out Burke, then it prints out Burke, and then there is a space here. You just can't see it because it's white space. Let's do that once more. But I'll go ahead and append my first full name to this. Right? And you see that it appends. What if I did this many times? All right? I don't know how many that is, but do you think it's going to work? Let's find out. All right. Oh, what happened? I did it just enough times to force this to happen. Segmentation fault. Why? I went past 100. Remember that this was of size 100. So effectively, how many characters can I actually store in there? Only 99 because I need an extra space for that null terminating character. This was way too many. You can't append that many and get away with it. So let me go ahead and reduce it down to 1. Right, there we go. And I'll go ahead and cut and paste this as an example. Right? And then we'll note, again, the usage of this. Oops, not twice. Come on. There we go. All right. So STRCAT concatenates the second argument to the end of the first. Right? It is your responsibility to ensure that the second or the first argument is big enough to handle whatever you concatenate. And did you see me? Let me go ahead and responsibility. OK, there's no spell checking, so responsibility. There we go. And not full code. Come on, really. There we go. Go back down. There we go. All right, it's your responsibility to make sure that the first argument is big enough to handle whatever you're trying to concatenate. And like I just showed you, it was not that 100 sized array was not enough to hold 50 copies of my first name. And so you get a segmentation fault. If you're lucky. If you're unlucky, you'll simply just get undefined behavior and start screwing up your own memory somehow. So you got to be careful there. Not only that, but did you see me handling manually the end of the null terminating character? Nope. So STRCP or STRCAT handles the null terminating character for you, right? In general. Now, if either one of those arguments is not null terminated, it's not going to know where the end of this first string is in order to add this string, and it's not going to be able to know where the end of this string is to stop copying over those characters. So like everything in the string library, it assumes that you're giving it valid null terminated strings. And if you're not, then it's going to run amok and start rewriting memory that doesn't belong to you. Right? There are also size limited versions. Right? So STRCPY and STRCAT both have byte limited versions, or length. I'll call them length limited versions up here. Versions called STRNCPY and STRNCAT. So it's got an extra n in here, and it's got an extra argument that you give it. Basically, you can give it another, I think it's a third argument. Not it, but them. You can give them another third argument that limits how many bytes, that is, how many characters, are copied or concatenated. Right? So let me go ahead and give you an example. Again, do this by example. Let's go back over here to this. Instead of appending the entire thing, Christopher, say that I only want to do the first 5 characters, my shortened name, Chris, onto the end of this full name. Well, I can go ahead and change this. Instead of STRCAT will concatenate the entire thing. STRNCAT will only limit it to a certain number of bytes. And as you can see right now that it's complaining because there are too few arguments. You expected 3. This is the destination. This is the source. And then you need to give it a limit. I only want to copy at most the first 5 characters. Right? And now this is happy to do it for me. Hopefully this breaks. If not, I'll tell you why it should break. There we go. And you see that it only copied CHRIS, the first 5 characters. Unfortunately, it didn't break because what I'm getting at here is that it does not handle that null terminating character for me. How would I know that? I would RTM, STRNCAT. Let's look that up. STRNCAT. And when I zoom in, if the length of the C string in its source is less than the number, only the content up to the null terminating character is copied. But if it's, let's see, where is the null? Appends the first num characters to the source and destination. Oh, plus a null terminating character. All right, there. I'm glad that I RTM'd because it is handling the null terminating character for me. Right? I didn't know. Okay, my memory was not serving me well. So plus the null terminating character, it handles that for me. Yeah?
I think the reason that you're not remembering it right is because that was C++.
Good catch. STRNCAT. So let's go right to the source, the actual man pages here. Let's see what it says. Appends the source to the destination string, overriding the null terminating byte at the end of destination, and then adds a null terminating null byte too. Okay. All right, so be it. It's doing it for us. Source does not need to be null terminated if it contains n or more bytes. Blah blah blah. It will use at most n bytes from source, and yeah, it handles the null terminating character for you. Okay, I was wrong on that. RTM, read the documentation to be sure. Let me go ahead and cut and paste that so that you have it for your examples. And of course, let me do one more here. STRNCPY. You can also limit the number of bytes there. So, for example, if I only want BOU, I'll limit that to 3 bytes, right? And run this, and you see that it is BOU, and then, of course, it doesn't make any sense. That's not a shortened version of my last name. But you can limit the STRCPY or STRCAT. Okay? And I'll include that in the notes there. Okay? Okay, that's concatenation. What about substrings? Right? Often, you'll want only part of a string, right? Called a substring, right? So, for example, if you've got this string here, and then I just want this part right here. I want the hello world, how are you? Maybe I just want the world in that. So, for example, let me go ahead and come over here and have a message instead, or message. And I'll use elision here so that I don't have to specify how large it is. Hello, world, how are you? Right? And end it. There we go. I don't want that colon. All right. And then a char word. Right? And I want my goal here. Goal is to copy the world part of message into Word. Right? So by copying, I mean I want the character starting here, and I want it to copy all the way over there. So I want to start my indexing where? HELLOW. So how far over is this? That's a 0, 1, 2, 3, 4, 5, 6. So what I want to do is I want to start at message of 6 and copy 0, or this is 1, 2, 3, 4, 5 characters. Right? So how could I do that? Well, what if I did this? What if I just went strcpy into message word, and then I printed it out? Printf, the word is equal to %s and the line word. And by the way, I need to make this big enough, so I'll just make this of size 100. Right? And if I ran this, well, what would it end up copying? Come on, run. Whoa. Oh, message into Word. Sorry, that's backwards. I want to copy into Word message. There we go. All right, there we go. So Word is equal to hello, how are you? That's not what I want, right? First of all, I want to limit it to 5 bytes. So what technique did we just see that I can use instead of strcpy? I can use strncpy. Right? And I will provide, say, 5 bytes. But that's still not going to work because it's only going to copy over, come on, hello, because it's going to start at the beginning. So this second part, how can I start at message of 6? Well, I could start at message of 6 here, except that it's complaining with this green. Does green mean good? Oh, no, it does, but it's not as bad, right? It's just a warning, incompatible integer type. So let's see what it actually does. I don't know. I don't know what it's going to do. Segmentation fault. Right? Now, why is that? What is message of 6? We already said that it was capital W. Well, what is capital W? ASCII table. Capital W is, I have no idea. Capital W is 87, right? A string is a memory location. So does the memory location 87, memory location capital W, does that belong to me? May not even exist, right? So that's not what I want. What I want is the memory location starting at this thing over here. So if this is a character, right, a char, this is a regular old char, how do I make it into a char star? How do I take a char and make it into a char star? How do I take a regular old variable and make it into a pointer variable? What do I need to put in front of this? The referencing operator, which is the ampersand. Right? Remember that a character, an array is nothing more than a pointer. Message right here is a pointer pointing to the memory location starting at capital H. Well, if I go over 1, 2, 3, 4, 5, 6, right, 6 over, then that's a new memory location. I simply need the memory location starting at that capital H. And by putting in an ampersand here, that's exactly what I get. And I get the world instead of hello. Right? So how do you do substrings? Well, you need to start where you want to start by using an ampersand here. And then if you only want part of it, then you need to specify, well, how big of a string do you want? 5, say. Right? Now, all of these have been toy examples, but when you get into your hacks, say I think on Thursday, that's it. Thursday is your hack session. If you're processing, say, a DNA string, and you want to look at a substring of your DNA, you've got this protein sequence or something, a bunch of A's, G's, C's, and T's, and you want to splice that DNA up. You want to look at a substring. I only want to look at this part of it because that makes a certain protein, or this makes a certain protein. I want to split it up. Well, you can do this by the thing that you want to do is look at substrings instead, substrings of a certain size. I'll go ahead and put this into the notes as well. So there's no built-in substring. A lot of languages do have built-in substring functions where here's one string, I want the string starting at index 5, or I want the string starting at index 5 and of a length something. It'll do that work for you. With C, you have to use your own ingenuity to do that because it's not built into the string library. You can always write your own functions to do it, though. Right? Okay. Some more convenient functions. Convenient functions. There we go. So there's another library that some of you have already been using, and I think I've mentioned it before, called the C-type library. Right? The C-type library provides some more functions that operate on individual characters. For example, you have things like isAlpha int C. All right. Don't worry about. Let me go ahead and change that to a character. Don't worry about integers, characters, whatever. All of these are actually going to take integers, I believe. But again, the ASCII text table, a character is an integer because a capital W has a value of, what did we say, 65 or whatever it was. So isAlpha returns true if the character that you give it is A through Z, capital or lowercase. If you give it an exclamation point or something, that's not going to be an alphabetic character. So isAlpha, or you've got isUpper, or is lower. Let's see. Or you can convert. You can do something like to upper of C, or to lower of C. So if you have an uppercase character and you want to convert it to its lowercase character, you can hand it off to this function, and then it'll return the uppercase version. These are also convenient because even if you have like an exclamation point, there's no such thing as an uppercase exclamation point. It'll simply just return the exclamation point back to you, so that you can just blindly go through and say, change everything to an uppercase letter. Right? Very, very convenient. Others include, say, is space. Right? And that'll return true if it's a tab, an actual space character, an n-line character, a line feed. It's anything that can be interpreted as white space characters, not just a single space. You also have, say, is digit. Right? So is it 0 through 9? And there's no lowercase or uppercase there. And that's just a very small sampling of what's in that library. It's all in the C-type library. And it just provides convenient functions for you to determine, is this an uppercase character? If so, I can change it into a lowercase character, etc. Right? All right. You also have string formatting. So recall that printf, and let me put that into code here, prints a formatted string to the standard output. Right? You can use another function called sprintf to print, and I put that into quotes here because you're not actually printing to the standard output, but you're printing to another string. Right? What do you think the S stands for? String printf. Instead of printing to the standard output, you're printing to another string. All right? So again, let me go by example here. Let me go ahead and I'll just use message here 100. There we go. And let me go ahead and create some more variables. Int x is equal to 42. Let's go with pi. Double pi is equal to 3.1415 159. There we go. And another string here, name, char, name is equal to Chris. And what else do we want? Oh, that's good enough. So what I want to do is I want to print to a formatted string. Let me just go ahead and do that using printf first to show you again how it can be done to the standard output. Printf, x is equal to %d is the placeholder for an integer. Then let's go ahead and print the variable pi, but only out to 2 decimal places. %f, is that going to give me 2 decimal places? No. So what can I put in there instead? 0.2, right? In fact, we'll go ahead and do at least 4 characters. So that'll be 3.14. Actually, no, so that's going to be normal. Let's go ahead and go with 10. I'm going to pad it out with a bunch of spaces over here. And then my name is %s is the placeholder for a string, right? And then we'll end the line. In fact, let's go ahead and tab over, too, just to show you that we've got as much as we want here. X, pi, and name are all going to be printed to the standard output. Okay? And let me go ahead and bring that over here and redo it so that you see there's a tab over, and then X, and then it printed 42 formatted as a decimal. Pi, 10 columns here, only out to 2 decimal places. And then, of course, this with going to the next line. All right? So that does it to the standard output. What does it look like if I want to print it to a string, s? Right? Now it's going to complain here because sprintf has a different formatting. Let's look it up. RTM, read the documentation. Sprintf. And it's OK that this is C++ here. So the format is actually the second argument. And then all of your various arguments that you want to print, those are going to follow. It takes this new first argument, the string that you want to print to. So let's go back over here to REPL, and I want to print to this message. So I'm going to go ahead and put in message here. Now when I run this, I expect no output, because did I actually print anything to the standard output using printf? No. I took that formatted string, and I put it into this string, which exists in memory. And I'll show you that you can actually see the results here by using regular old printf, %s, and the line. I'll just use this message. And you can see the same results as before, right? That the exact same formatting here, but it's not, the sprintf is printing it to a string so that you can store it, and then you can process it later if you want to. There are several versions of these. Printf is just always going to the standard output. Sprintf is going to print to a string. Fprintf is also available. What do you think F stands for? File. You can print to a file instead. Right? Instead of the standard output, you can dump stuff to a file, and now you're doing file output. That's why file input and output are one of the easier things in C, because you've already covered everything. Printf, all you need is fprintf, and you're good to go for file output. Okay? Let's see. All right. So again, sprintf takes one new argument. The first argument is the string you want to print to, right, instead of the standard output. Right? Again, it is your responsibility to ensure that the destination string is big enough to hold the results. Right? So often it's going to involve you making some pre-calculations of, is this big enough? Well, if it's not big enough, then I can't print to it. So one workaround is just to make it big enough, right? I anticipated that, well, if 100 is not big enough, go ahead and make it 1,000, right? Now, you are abusing the stack space here, but not that bad. 1,000 bytes is not that big of a deal. It'll be cleaned up when you return from a function or whatever. But if you are doing this as a matter of course and you want to make your code less brittle, this is very brittle code. This could break very easily if, for example, my name here was over 1,000 characters. Right? It's not likely to happen. That's why I overshot it and overestimated how much room that I needed. But it is brittle in that it can still break. Right? You could write past the end of this string. So you have to be careful. Okay? That's string formatting. And the final one that we're going to look at today is string tokenization. There we go. So often, data is formatted. And some of the simplest formats that you can look at are CSV files and TSV files. So anybody know those acronyms? What is a CSV file? Often you'll come up with this when you're working with Excel or something like that. So CSV. Anybody? Comma, separated value file, right? And you can open up a CSV file. In fact, generally, if you've got like a CSV file, you double click it, it generally wants to open it up in Excel because that's kind of the default thing to do. A comma separated value file is simply something that looks like the following. Example. Let's go with, example. For example, if I've got a string that has Chris, comma, I won't have spaces in the Burke. My NUID 35140602, something like that. Whatever. Maybe my city, my office number 363 Avery Hall. Right? And so you can have spaces in there. You just have to be careful that each one of these things is a token. Right? Each piece of data, oops, let's close that off, is separated by a token. Now, in a comma-separated value file, that token is a comma. In a TSV file, that token would be what? T. What do you think? What kind of character T? A tab. It's a tab-separated value, right? Comma or tab-separated value file. And I don't know, it's far more common to have comma-separated value files. But what's one immediate drawback here? What if I want a comma in my data, right? So Omaha, say, Nebraska. Maybe this is all one thing, one token, right? And you have a comma in there, right? Omaha, Nebraska, where I live, right? Well, it could be interpreted as Omaha, comma, Nebraska, city, comma, state. Or maybe it's like an entire token that should be treated as one thing. So the problem is ambiguity. What happens when you need a comma in your actual data? Well, what's one solution? Okay, you could escape it, right? And now you have to tokenize and make sure that, okay, here's a comma, but it's preceded by a backslash. So this is not a token, and I need to skip it and go to the next thing. Unfortunately, it's not going to work like that for us with the standard C library doing this. Instead, if you want to get that sophisticated, which is not all that sophisticated, but if you want to get that sophisticated, you need to bring in a library to do it. All right? What we're going to be looking at is very simple ways of tokenizing data. So we'll stick to simple data tokenization. What we're going to want to do is we will want to split a string along some delimiter. And again, usually that's going to be a comma. It can be other things, though. And process each token separately. Right? So we don't have to reinvent the wheel here. There is a function that will allow us to do this. And the function that we'll use is STR. Now, if you want to tokenize something, what do you think? String tokenization would be toke, right? STR toke, okay? It takes STR toke. It takes two arguments. The string you want to tokenize, and a delimiter that you want to use, okay? Generally, we'll only use one delimiter, but you can use multiple ones. For example, if you've got, say, semicolons are a subdelimiter, that address, right? Comma, 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 those are my main tokens, and then I've got my address here, street, city, state, and zip. I could have further subtokens in that using semicolons or tabs or something else. And if you wanted to split it up along all of those tokens, you can do that. We're going to keep it simple, though. We're going to keep it simple by only looking at one delimiter. I want to go through this string, and I want to print out, say, Chris. Then I want to go to the next string and print that out, or do whatever you're going to do with it. Print out the next token, the next token, the next token, etc. Generally, the token, or the delimiter, delimiter is ignored. Delimiter is ignored. Right? The first time, it has a little bit different operation than the functions that you're used to. The first time you call strtoke, you pass the string you want to tokenize. Each subsequent call, in order to continue tokenizing the same string, you need to pass in null. Because if you pass in another string, or if you pass in the same string over and over and over again, it'll simply start at the beginning of the string, giving you the first token. Pass it in again, it'll start at the same string and give you the same token. If you give it another string, that's when it knows that it needs to restart the tokenization process and tokenize that string over there. Right? So to tell it to continue where you left off, you need to pass in null. And I'll give you a demonstration here of all of this in a second. In fact, on this piece of data. But the last thing to realize is that, keep in mind, strtoke will change the contents of your string. So if you want read-only data, you're going to have to make a deep copy of it and hand that off to the tokenization process, because it will change the contents of your string. In fact, let's look that up, strtoke. How do I know that it will change the contents of my string? Here's the string that you want to tokenize. Here are the delimiters. It's not going to make any changes to the delimiters. Why? Const in front of it. Do you see a const in front of the string that you want to tokenize? No. That's C's way of telling you, yes, this string is going to change. Okay? Let's take a look at an example. I'll just call it data, and I'll set it equal to this thing. All right? So there's my name, NUID, et cetera, et cetera. We need to take or process the first token. Now to do that, I'm going to call strtoke. And I'm going to pass in data. That's the thing that I want to tokenize. And what delimiter should I pass in? What do you want to tokenize this on, at least initially? Comma, right? Note here that I'm using double quotes. That's because of the way strtoke is defined. Const char star. If you want to use multiple delimiters, for example, I want to delimit on spaces and lowercase i's and lowercase e's. It'll do that for you. It'll treat those all as tokens. Or something more sensical, I want to do commas, semicolons, and tabs. All of those are going to be my delimiters. It'll simply go up to the next delimiter, one of those three delimiters, and say, this is the next token. Then it'll skip to the next token, skip to the next token, skip to the next token, each time you call this thing. Okay? Now, there is a problem. Let me go ahead and just go with commas for now. Now, there is a problem. Well, how do I get that token? Right? Let's go back over here to STR token. What is its return type? Char star. It returns a pointer to the next token. Here's the first token, then the next token, then the next token, then the next token. I need to capture that return value. Right? So let me go ahead and create a variable to do that, char, and I'll call it toke, or n. All right? There we go. And I will capture that value. Let me go ahead and print it now. Printf, %s, and the line token. So what's the first thing that it's going to print? Well, my first name. Because it goes and sees, OK, here's the token, and here's the delimiter, so this is what I'm going to end up returning. Right? Now, if I call it again, let's go ahead and try calling it again with the exact same parameters here. What's it going to print now? Probably the same exact thing. Why? Because I gave it the same string. It says, OK, I'll go ahead and start tokenizing from the beginning of that string, beginning of that string, beginning of that string. If you want to continue tokenizing on the next token over here, you need to pass in null. Keep going on the same string that you were working on. So that where did it leave off working? It left off working right here. So that the next token will be now my last name. OK? Well, I can go ahead, cut, paste, cut, paste, cut, paste. This is a huge red flag, right? How many more? There's Chris Burke, this, Omaha, Nebraska, and then my last one here. There we go. There. And there's the last token. Huge red flag here of copy pasta, right? I probably shouldn't be doing this. If you want to do this, what would be a better way of doing this? Probably going into a loop of some sort. But the problem is, how do I know when I'm going to stop? What if I go one more? Did I go one more already? Okay. That's definitely at least one more. What's going to happen here? Ah, null. So how do you know that you stopped? So it processed this token, this token, this token, this token. Finally, this is the last token that it processed. I went one more. Was there another token after that right here? No. So what was the only thing that it could return to tell me that there's no further token? What? Null. Right? So that tells me that I could write a loop for this instead. Okay? I'm going to go ahead and do the first one because by itself because I don't know how many tokens there are going to be. So I'll go ahead and write a loop here. While something, I will continue tokenizing. Give me the next token. Give me the next token. Actually, I'll leave it like this for a second. Okay? There we go. And get rid of all of these other print statements. What condition do I want here? While token is equal to null, is that going to work? That's my stopping condition. So if you want a continuation condition, you need the opposite, the negation of that, which is going to be not equals. While the token that you're reading is not null, this is not null, Chris is not null, Burke is not null, this number is not null, city is not null, NE is not null, and then finally this is null. But after I'm done, then it becomes null, and I break out of that while loop. Let me go ahead and run this. This is the first token is done outside the while loop. That's where I'm printed right here. And then the last token, of course, is null because I'm printing it afterwards. If I wanted to, I could have skipped. I could have put this up here, and now this will print all the tokens, but not print that last one. So the last thing I do in the while loop is the thing that I set myself up for the next thing in the while loop, or for the next iteration of the while loop. All right? The order of a while loop matters, remember. And why did I use a while loop instead of a for loop? I could have used a for loop. For, and then token is equal to this thing. There's my initialization, right? Token is not equal to null. And then my continuation, my update would be this thing. This is called a sentinel loop sometimes. And then I don't have to have it there. There we go. Oops. Token is not null. Why is it only doing the first one? For I equals, well, I is continue. No, not equal to null. I'm doing something wrong there. Oh, well. Well, you see how brittle it is. I'd have to think about that for a second. But also, the point that I was trying to get across there was that readable? All that crap shoved all together? No. This is far more readable. This is your initialization condition done before the while loop. This is your continuation condition. And then this is your update, all on separate lines, much more readable. And I'm using a while loop because I don't know how many tokens there are up front. I could have another token here, hello, foo, bar. And it'll still work if I add more tokens. If I have fewer tokens, I'll go ahead and take away my address there. There we go. And what if I have empty tokens? This is a good question that usually comes up. I have one, two, three empty tokens here. Does it print it or not? Nope. It ignores all runs of delimiters, skipping all of the empty tokens, including n tokens here. There we go. Right? So it skips all of the anything that's empty. And if I put them at the beginning too. Right? There we go. I could, again, put multiple delimiters here. Say that I put in, what's common here? Lowercase, no. I'm looking at, let's see, what else is, oh, here we go. There, and now, oops, I need to do the same thing down here, O. And now you see that foo wasn't processed because a lowercase o is now one of my delimiters. Right? And then also, my last name was broken up because there's a small o in it. And it's just B and then the rest of it. Okay? So let me go ahead and restore it to a sensible example here. And I will make sure that this is in the notes. So that's a string process. And again, I'm only looking at a very small part, the most useful parts of the string library. There are dozens upon dozens of different functions in the string library that you're free to use, that you're free to adapt in any of your exercises or in any of your homeworks or anything like that. Right? I think that's all I had. Oh, one last thing, sorry, that gets us into a later topic. Don't worry about this topic just yet, but string comparisons, revisited. So, again, in C, you cannot use the equals equals operator, TOR, to compare strings. Equals equals is a numerical operator. Using it with strings. What are strings again? They're just simply char stars. Is only comparing the memory addresses of strings, not their content. So for example, let me go ahead and grab this example and go back over to REPL here. And I'm creating two strings of size 10, just big enough basically. I'm copying in Chris into A and Chris into B. And then I'm asking, are these two strings the same? Now conceptually, are these strings the same? Conceptually, yeah, they have the same content. But remember that I've called malloc. The first Chris, the A Chris, is pointing to some memory location over here. Another call to malloc makes it so that it's a deep copy of a different memory address. So is this going to print there equal or nope? Nope. Why? Because they're different memory addresses. You cannot use equals equals on pointers. Well, I mean, you can. You're just asking a different question. Are these pointing to the same thing? Well, in this case, no, they're not. If I did a shallow copy, say A, instead of this, now what's it going to print? Yes, because they're equal, because they are now pointing to the same memory location. I made A, and then I made B point to the same memory location. That's a shallow copy. So if you're looking for deep copies versus shallow copies, yeah, go ahead and use an equals equals. But what I'd like to do, and let me go and back this up, what I'd like to do is I'd really like to ask, what about apples and oranges? Right? Which one of those comes first? Well, first of all, are they equal? Certainly not, but that's a correct answer, but it's the wrong way of getting to that correct answer. So which one of those comes first? Which one would you put first? Apples. Why? A comes before O, right? Let me go ahead and take this and this. There we go. So in order to compare, I need to use a different function. Okay? To properly compare strings according to their content, you need to use a function. And this is our first function, the comparator style function. It's not an actual comparator. We'll talk about that later, but it compares strings. So what do you think it's called? STR Compare. What would be the sensible three-letter shortened form of that? CMP, right? STRCMP. It takes two strings, right? And of course, they have to be null terminated, et cetera, A and B. And it returns something negative, 0, or positive based on the relative ordering of the string contents. Right? So if A is less than B, this is conceptually. And conceptually already you told me that apples come before oranges. So A comes before B. Then it returns something negative. You cannot read, and some languages you can read something into the magnitude of that, but in C there is no standard that you can't read any. It could be -10, it could be -1, it could be -42. There's nothing that you can read into that. If A is equal to B, that is again conceptually. That is, they have the same content, apples and apples. It returns 0. Right? So this is even better than simply not equals or not equals. Because if you're only looking for equals and not equals, you can only get this answer down here. It's equal or it's not equal. It's 0 or it's not 0. But this tells me a lot more. If A is greater than B, in other words, they're kind of out of order, conceptually, it returns, again, something positive. Okay? So let's go ahead and see this in action. What I'm going to do is I'm going to call I'm going to create a result here. R is equal to STRCMP. I'll compare A to B. And then I'll print out the value of that thing, R. So you already told me that apples comes before oranges. So what's this going to print out? Are they in order or out of order? A, B. Are they the apples come before oranges? So A is conceptually it's less than. So it should return something negative. There, negative 14. Again, don't read anything into that actual number. What if I switch these around? What if I put oranges up here and apples up here, down here? Apples. Okay. What should it print out now? Something positive. Not positive 1, maybe positive 14. I don't know. That is 14. Maybe there is something you can read into this. But you'd have to RTM, read the documentation. It's not standard. Right? Okay. Well, what about apples and apples? Now you're comparing apples and apples. So what should it print out? 0, right? They're the same string. What about apples and apples with a capital A? Are they the same string? No, they have different content. Capitals and lowercases are not the same characters. So which come first, capitals or lowercases? I still have it open here. Zoom in. Where are the capitals? Starting at 65. Where are the lowercases? Starting at 97. It's all lexicographic order. It is not dictionary order. Right? So it's lexicographic order. So which one of these comes first? Capital A apples. I'll put them all caps there. Capital A apples comes first. So are these in order or out of order? Out of order. So you would expect something positive. 32. Okay. What about apple and apples? There we go. Which comes first there? Now, think about dictionaries now. If you had apples and apple, which one would you put in the dictionary first? The shortened one, apple, right? The singular form. And so these are in order. If they're in order, it would return something negative, negative 115. Again, there's nothing that you can read into that in general. Right? So why does it work like that? Well, what character is actually here, right, to compare to the lowercase s? The null terminating character, which always comes first. And that's why it works lexicographically like this. What else should we compare here? What about apples and zebra? Which comes first? Oh, zebra. Why? Because it's a capital letter, the way that I wrote it up here. Remember, it's not dictionary order. If this were dictionary order, then apples and capital A, apple, or whatever, that would be in the dictionary up here. And then zebra, regardless of the uppercase, lowercase, whatever, would be down here. But it's lexicographic, so it's going to say that it's out of order. Zebra comes first. Capital Z, zebra comes first. What about 1, 2, 3, 4, and let's say 98. There we go. So, well, 1,234, that comes before 98, right? Well, here, let me just simplify this. 199. 99 comes before 100, right? So you'd expect this to return something. They're in order. They're out of order. So you'd expect it to return something positive. It's actually something negative. Why? These are not numbers. These are characters, right? 99, the number, I agree. That comes before 100. But 99, restrict your attention to this, to the first two characters here. 1 and 9. Which one comes first? Where are they? There. 1 and 9. Which one comes first? 1. So it doesn't look any further. It says these strings are different, and 1 comes before 9, so therefore they are in order. And I'm going to return something negative, in this case negative 8. Okay? This difference might actually be the difference in their ASCII text table value. Right? That's what I'm suspecting now. Right? So you have to remember, it's lexicographic. It's not dictionary order. It's not numerical order. It is lexicographic order. It looks at the two strings until it finds the first difference. At the first difference, it says, it goes to the ASCII text table and says which one comes first. If you want different behavior, you're going to have to implement that different behavior. There is another example I can give you, STR case CMP. So apple and, I'll go with apples and apples. Right. Now, case is simply just STR case CMP. It's a terrible name, but it's a case-insensitive version of this. So ignoring cases, uppercase and lowercase, are these the same string now? Yes. Uppercase A apples and lowercase a apples, and it's going to return a what then? If these are the exact same strings, ignoring case, then it's going to return 0. And you can do, this is actually an exercise that you'll do, I think, in one of your, not your third homework, in your fourth homework. Apples, there we go, right? The SpongeBob meme speak, right? There we go. And they're equal, right? So yeah, you're given an exercise where you're given a string, you have to go and you'll have to alternate uppercase, lowercase, right? So there you go. If you ignore the case, then of course these are the same thing, okay? All right. I will go ahead and make sure that all that gets in there when I post the notes. Any questions so far? Because I want to change our attention just a little bit. Usually we wait until after you have something substantial, for example, arrays, to introduce you to more formal debugging. Now, up to this point, you've probably debugged using printf statements. Or a lot of you were asking about that. Some people online were asking about that tool I was using to visualize stuff. Because, man, that's cool. I can see where I'm going wrong, and I can put that in there, and I can check it out and see and visualize my code step by step, or at least slow my code down and look at what each one does. Well, that's what a debugger is for. Printf statements are what's called a poor man's debugger. Right? If you can't afford a debugger, then go ahead and throw in a bunch of printf statements and go ahead and go that way. The proper way of doing that stuff is using a tool called a debugger. A debugger is nothing more than a program that runs another program and allows you to stop, right? You can start running the program, and then you can step line by line through the program. And then you can check and see, well, what is the variable value now, and what is, okay, now go to the next line, what is the variable value now? You can see the changes in your program line by line. You can jump to another line. You can go ahead and continue operation until it gets to that line, so you don't have, if you've got 1,000 lines, you don't have to go through 999 steps just to get to that last one. You can jump to that last step. All right, yeah?
This requires that you still have successfully compiled it with
Yeah, you still have to compile. That's definitely the first step. If it doesn't compile, then you're dead in the water. But you compile differently, right? So you can set breakpoints, you can jump to a certain line, and the one that I'm going to show you is GDB. GDB stands for GNU's debugger, so DB, debug, right? It's a command line debugger that gives you a lot of control over your stuff. I'm going to demonstrate the basic usage today, and then I'll show you a fuller example on Wednesday. But the big thing is you do have to compile differently. You have to use this G flag. Don't ask me what the G stands for. It should be like debug or D flag or something like that. I don't know. But it stands for GNU's debugger. Now, the reason that you need to use this flag is because when you compile to machine code, if you named your function my awesome function, yay, right? Does an actual machine care that you named your function that? No. All those symbols are thrown out. And it's just a bunch of machine code. It's just a bunch of zeros and ones that now are meaningless to us. But I want to see my functions because I don't want to just see a bunch of binary. You can't read binary, all right, unless you're really talented. And so you need to use this G flag that preserves all of those symbols. It keeps all of your variable names. It associates all of your function names and stuff like that. Now, the bad part about this is that the standard library, you can't jump in there because all of those symbols are gone. You'd have to take like the standard library from scratch and recompile everything with this flag if you really wanted to dig deep into there. So you're not going to be able to use this debugger to jump into, say, printf or jump into square root and see why it's not working. You just assume that the standard libraries are bug-free and that the bug actually lies with your stuff. That's not 99% of the time that's true. The 99.9999% of the time that's true. That 0.000001% of the time where it actually is a bug at the system level, then that's where you have to escalate that and you have to report that to somebody else because you're not fixing that on your own. Right? But if you use the G flag, then it will produce an executable with everything preserved. Then to start GDB, you start it from the command line. You will have to do this on CSE unless you've installed GDB on your own machine. So be careful, but it's command line usage, so it doesn't matter. And then you can run your program. I'm going to demonstrate this now. I've got a buggy program here. I'll show you what it looks like, first of all. There are lots of bugs here, lots of intentional bugs. Right? So I create the first sum primes or whatever, and I'm going to sum them up. This is an exercise that we've done before, but I've introduced a lot of bugs here. And when I run this, okay, GCC -G, array, whatever. All right, great, no news is good news. When I run it, got stuck somehow. So what's wrong? What's going on? What? I'm in an infinite loop. So that's the first thing that we're going to take care of. If you are stuck in an infinite loop and you don't know where, you might be tempted to start going in and, okay, printf statement, I'm okay up to here. Printf statement, I'm okay up to here. Printf statement, I'm okay up to here. Don't do that anymore. Once you've used GDB, you won't go back. GDB a.out. Now that just starts up GDB. It's not started my program. To run your program, you can go run. Right? Don't worry about that other stuff. Okay, you see that it's stuck in an infinite loop. I will go ahead and, how do I kill an infinite loop again? Control C, right? And lo and behold, what does it tell me? You're caught in an infinite loop around line 35. Right? In fact, here's the line number, right? Okay, I can go ahead and step to the next line. Next, 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 and you see already what's going on. I'm not incrementing I, right? Next, next, next. In fact, next, you don't have to type that the entire time. N. You see that I'm stuck in an infinite loop here. And looking at only one line, that gets kind of strainful on the eyes, I guess. So let me go ahead and go out layout next. And ooh, I see my entire program up there. Next, 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 next. Right? And you see that I'm caught in an infinite loop. Now, if you see this, it's obvious now that because it was a really intentional, obvious problem that I'm missing a ++. I'm not making any progress towards my terminating condition. Well, what value does I have? I can print I, right? 0. Why? Because, well, it was initialized for me to 0, and I'm not making any progress. Okay, something's fishy here. I can print total, right? Well, it's overflowed now, right? It's some nonsense stuff. But I can continue. Go to the next line, go to the next line. I can even continue. Of course, continuing, I just go back into that infinite loop, right? I'll kill it again, and I stopped it right there. And I can, okay, well, obviously I need to fix this. So let me go ahead and quit out of this. Array debugger, and we found our first bug. My first bug was that I didn't have the ++ here. Right? That one was pretty obvious once we saw it operating in a debugger. I'll go ahead and compile it again, because, and okay, well, now it's actually running, but am I getting the correct answer? The first, however many primes were there, was the sum 7? Nope. So I've still got a problem here. GDB a.out. Now, if I just run, well, okay, it's just going to print out total 7. I want to see where, I want to isolate where the problem is. So I want to start the program, but I want to walk through line by line to see what's going on. So again, I'm going to go with layout next. We'll cover all this again on Thursday. And if I start it, if I just run it, of course, it just ran through all immediately. So what I want to do is I want to stop at this line right here. I'm going to put what's called a breakpoint in there. Break at line 14. What that does, and you can see that there's this B plus now, that's a break. If I run this, it'll run up to that line and stop. You can put as many breakpoints as you want. I want another break at line 25. To get rid of a breakpoint, break 25, or clear 25. I think. Nope. All right, refresh. Oh, 26. Clear 26. Because line, there we go. Clear. There. Oh, I cleared all of them. All right, that's not what I wanted. All right, so rerun this. Break at line 15, run. All right, I'm run from the beginning, yes. Okay, there we go. I've got my, oops. Sometimes it screws up. You see I've got 2 line 15s here. Refresh, does it? There is a quick key for that, but I forget what it is off the top of my head. But you see that I cleared out those breaks. You can clear out whatever breaks you want. Note that when I said break at line 25, did it give me a break at line 25? No, it gave me a line at the next available line because there's nothing to break on line. There's no command on line 25. So okay, I'll go ahead and go next. Oh, okay, next. Wait, what about primes? Was primes initialized correctly? Let me print primes. Well, it's a memory address, right? Is that a memory address that belongs to me? What's in there? I'll go ahead and go next. Well, 2 should be in there now, right? Print primes of 0. It should be 2. Okay, well, all right, that's fine. Print primes of 1. Well, what's in there is 0 because I never said it. Next, 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 next. And it's not showing up. What was wrong? By the way, you can't back up. You can't go previous, 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 previous. That's not possible because it would have to save the entire state of a program at each stage of your, it'd have to have an entire save state here in order to go back to it. So you can only go forward. But you can always restart, run from the beginning, yeah, okay, and refresh because it screwed up again. So what was the problem? What am I doing there? Print primes before. That's the memory address. If I'm calling malloc, it should be giving me new memory, right? Next. Print primes. Is that new memory? That's the old memory address. That's the new memory address. What happened here? Or what didn't happen on line 17? I didn't set it equal, right? I have primes here. What's it pointing to? I don't know, whatever that is. That thing right there is. Then I called malloc that gave me new memory. What did I do with it? I forgot it right away. Right? I have a memory leak here. I needed to make this pointer that was pointing to whatever, I need to make it point to that new memory. So I can see my error right here. Right? Quit out. I would have seen that. It would have been pretty obvious if I had followed good programming principles and good practices by initializing it to null. Now when I do this, immediately seg faults out. Why? On this line, what am I doing? I'm dereferencing a null pointer, so slap yourself over the head for it. And when I run this on GDB, I see it now, run layout, or layout next, right? And there was a seg, it stopped automatically here because there was a seg fault because primes is null, print primes. It's null, it's 0, right? If I try to dereference it, print prime, dereference primes and see what's in there, well, it cannot access memory at null. It doesn't seg fault in the debugger because it's just simulating the program. So I see immediately, okay, well, that's my problem there. All right, again, edit this. By the way, you generally do have to go back and forth. Once you see a bug, you have to go back and fix it, recompile it, reopen it up in a debugger. Being able to fix it on the fly is called hot fixing, and there might be a way to do it in GDB, but I'm not sure. Right. Run it again, run it, a.out. All right, still a problem here. Right. So just looking at the program, can anybody, if you see the problem immediately, if it's just immediately readily apparent, just go ahead and keep it to yourself as a spoiler for Wednesday. We'll continue this, and I'll cover more commands. This is all part of Module 9, which is next week, which is a really short module because of the break. But I have a much more extensive video on how to use GDB using a program similar to this that you definitely should watch.